Okay, welcome everyone. Welcome everyone to my talk about safe software for autonomous mobility with modern C++. But the content of this talk is also applicable to other fields, just as aerospace, where you also need safe software, and autonomous aerospace vehicles are also more and more in the rise up. So imagine that you're a C++ engineer working on some cool autonomous driving project, and your boss comes into your office and says, by the way, what you're doing needs to be safe. And that is what happened to me last year, and might also happen to some of you guys, especially if you work in autonomous driving. And this talk focuses on what can be done on the C++ language level to make a safe product. And it's based on the requirement of ISO 26262. This is the automotive functional safety standard. Other safety standards might have slightly different requirements, but most of the things here can also apply there. You see also a video that is not very well working about our use case with autonomous driving car. This talk is not about 99% of functional safety, such as building a safety case or safety analysis or formal validation. There's a whole world out there. We don't talk about that. We just talk about what can we do on the C++ language level to improve the safety of your application. Let me introduce some language for you that are commonly used in safety engineering to help you understand the next slides. So, safe means that the risk of injury or property damage if the system malfunctions is not unreasonable. And unreasonable depends, for example, how likely is an injury of a human and how bad will this injury be. I'll make a few examples. If an event is rather unlikely but the outcome is death of a human, then it's most likely not acceptable. But if an event is rather unlikely but you just get some bruises, if this event might happen, then it might be acceptable. If an event is very, very unlikely, but the outcome is death, it still might be acceptable. And the safety standards have tables in them that say which kind of injury is still acceptable with which probability. So there's no 100% safety. There's always some probability involved. Then qualified means that a tool or component or library is compliant to relevant safety clauses of a specific safety standard. And certified means that an independent third-party agency, for example, TÜV is very famous, has analyzed the system. And they do analyze the system based on reports that you produce. So they don't necessarily look at your system themselves. You will generate a lot of reports like code coverage, static code analysis reports, safety analysis reports, and they will analyze basically the reports that you generate from your application and determine if your application is safe or not. Or not if it's safe, but if it's compliant to the specific safety standard. So let's talk a bit about some high-level requirements for a modern C++-based product. You need to have a qualified tool chain, which means everything that you need to create and everything that you need to create your application and everything that you also need to create any kinds of reports that are relevant for certification need to satisfy the safety clauses of the safety standard. Then a second requirement, and that is in most safety standards, is that the application must be memory static during runtime. Because if it's not memory static, memory allocation takes a non-deterministic amount of time, and also a malfunctioning application could consume excessive amount of memory, causing a cascade failure of the system. Also, the system needs to be real-time, so execution time should be deterministic, and a high priority task should be executed first. And also testability we need to have. You need to be able to test your code so that you can prove that your code is actually safe. And this high-level exercise, this high-level requirements we will exercise on some examples. We will exercise it on the C++ compiler and standard library, the standard compiler, standard containers and exceptions, and threading and related software architecture, and failure injection. So let's first talk about the qualified toolchain. To run a safe application, you need to have a safe underlying base. So if your operating system is not real-time and not safe, you can never have a safe application. Further, you need to also have a qualified C++ compiler, because even if your application code would be safe, if the compiler generates faulty binaries, then your application will not be safe again. So also your compiler needs to be audited for safety. And then you also need to have a qualified C++ standard library so that you can use this standard library in your application. And these components are actually surprisingly hard to come by. So some companies already have a qualified real-time operating system. They might even have a qualified C++ compiler. But for example, getting a qualified C++ standard library is very difficult. I know for a fact that BlackBerry with QNX has a bundle of these three components and should be ready soon. I know Wind River with VxWorks and Green Hills with Integrity. They have a qualified real-time operating system. They have a qualified compiler. I don't know if they have a qualified C++ library. But surely they might also be working on that if you reach out to them and ask them. What is also important that every third-party library that you're going to use also needs to be qualified. That means in practice that avoid large third-party libraries like Boost or Poco, because you're never going to get that through a safety certification process. And third-party libraries which are qualified out of the box are very rare. There are some out there, but even if they're qualified to some safety standard, maybe it's not a safety standard that you want. Now let's talk about memory static operations on standard containers. Again, the requirements that we have is that the application must be memory static at runtime. No memory fragmentation should occur. That is something that is often forgotten. And you need to be able to reason about resource usage. You need to make sure that during the runtime of your application, you don't run out of resources, or if you run out of resources, that you have this case properly covered. And the challenges that we have here is that standard C++ containers allocate memory, and they allocate this memory using different strategies. Further, stack memory is very limited, and if you run out of stack, it's very hard to recover from. Even if you use memory pools, they can fragment depending on how you use them. And also you need to have proper tooling in place so you can trace the resource usage of an application during its whole runtime. I want to talk a little bit how we now approached some of these challenges. Our approach basically is to group containers in 4 different groups: in strings, vectors, node-based containers like SED-map and SED-set, and hash-based container like SED-unordered-set or SED-unordered-map. With SED-string, with our string implementation, we just use a compile time fixed size string with stack storage. And we have 2 flavors, one which silently truncates if it would overflow, and one that throws an exception on overflow. And that's very simple, and it's very nice to have because you have no memory allocation. And because strings are generally very small, it makes it well suitable to store on the stack. There might be other applications or domains where you have worked with huge strings, and this approach might not be that applicable, but in robotics in general you work with rather small strings. And they're very simple to use because you can copy them, you can construct them. No memory allocation happens because everything happens on the stack. Then the second group is basically the vector, and we created just a runtime fixed vector which allocates from heap on construction. And then you need to construct the vector before runtime happens. And this vector satisfies continuous memory guarantee, but unfortunately it's much harder to use because you're not allowed to construct it or copy it during runtime. So our string implementation, for example, is not copyable, so it makes it harder to use it wrong. With node-based containers such as SED-map or SED-set, you're much more flexible. because they always allocate memory in known chunks. So this is where we can use a memory pool or allocator framework. I have here a link for a very famous memory and allocator library, which you can, for example, base your work on and then tear it down to your needed feature set. That is what we did. Yeah, we started with it and then removed everything that we don't need and made sure that we can satisfy the certification process of this software. So pools are allocated before runtime. And then here comes a very important point on how to use these pools. Basically, we always allocate, or we have per type or per size, we have one different pool. So which means for a SCD map, which we store maybe an integer and a float, yeah, we have memory pools that just give us pairs of integer and floats. And which means because we're always taking equally sized chunks out of the memory pool and put equally sized chunks back, we never run into memory fragmentation. Yeah. And because you have pools and you can arbitrarily granularly work with them, you can really ensure that you have proper resource isolation to really prove that your system is safe. Unfortunately, with unordered set and unordered map, this doesn't work so easily because they have a different allocation strategy. So they need to sometimes allocate more memory to resize their buckets where they store the hashes. And so here you need to find a different solution. If we talk about memory static operation, we also need to talk about exception. Exceptions also allocate memory. But we have the requirement that the application must be memory static at runtime. Therefore, exceptions also must be memory static. And also one must be able to reason about resource usage. So you need to be able to reason about how many exceptions do I have in flight? What happens if I run out of resources? Do I have proper error mechanisms in place, or error handling mechanisms in place if I run out of resources for exceptions? As the main challenges is, and they might be not the same for all compilers, but throwing exception allocates memory on the compiler level. Standard exceptions allocate memory to store the error string. And also exception handling adds hard to track and hard to analyze execution branches to application. And that makes it hard to generate coverage reports that are necessary for safety certification. We have some solutions for these challenges. For example, with GCC, you can modify the behavior on how GCC allocates memory for an exception. And to do that, you need to replace 4 functions that allocate free the regular exceptions and allocate and free the dependent exceptions. This is quite tricky because these functions need to behave very precisely, and there are some intricate details that you need to know when implementing these functions. But to make your life easier, we have an open source library that helps you with that already replaces these functions for you, and it also has a log-free memory buffer where then the exception memory is allocated from. And you can also then configure what will happen if you run out of exception storage. You also need to modify the standard C++ library to use a string storage which not allocate. And we're still working on that. We're working with providers of the standard library. If they do that, if we need to do that ourselves, that's still an open question. If you look at the tool support, I have here a quote from the JSF coding standard. That's the Joint Strike Fighter. That's the coding standard for the F-35 US military aircraft. And it's from 2005, and it says C++ exception shall not be used. And that's a safe real-time system. The rationale is tool support is not adequate at that time. And now we are basically, I think, 14 years later to this situation, and it's still problematic. And I can just show you one example here. We have a coverage report of a file, it says line coverage is 100%, function coverage is also 100%, but branch coverage is pretty low. And you might think, how can that be? And if you look, for example, at the code snippet down there, you see that we don't have any branches. We're just constructing to chrono nanoseconds or seconds, add them, return them. There should be no branches. But there are implicit branches created by exception handling. And alcov sees these branches. And the main challenge that you have now is that the safety standards for the highest safety levels, like ACLD, which what you need for autonomous driving is you don't have any steering wheel, you have no human that can stop a car from going off the road. So you need the highest safety level. You need to have 100% branch coverage. And I will talk a bit later on how we can use also C++ to improve failure injection so that we can actually try to cover these branches additionally. Now I want to talk about real-time and threading and the related software architecture. So in general, for a real-time system, your tasks need to have a deterministic runtime. Then execution of a task needs to be interruptible by a higher priority task. And lower priority tasks must not block higher priority ones. For example, everyone maybe heard about the Mars Pathfinder who exactly running this problem where a lower priority task actually blocked the higher priority task, made the Mars Pathfinder crash constantly, and they had to fix that then while the Pathfinder was on Mars. And the challenges here is that the standard C++ threading library only supports a very limited amount of configuration. So you need to have as well priority herd and CPU pinning, etc. Another challenge is that execution in C++ is not preemptible yet. So that makes it very hard to write any kind of real-time capable executor. You might find why I'm mentioning executors here. In fact, in robotics, most robotics frameworks, they rely heavily on executors. So if you talk about ROS2, they rely heavily on executors, and none of these executors is real-time. And it's also very difficult to ensure that multi-threaded code is correct because code execution is interleaved in a non-deterministic way. And if a data race occurs, the behavior of the program is undefined. So how did we approach these challenges? So we created a custom threading library, which is very as close as possible to the standard threading library to make migration of code and also let engineers learn it more quickly. But the difference are that threads are created during initialization and then they are put on hold until started for runtime using a condition variable. This is important because creating a thread during runtime is also not allowed because it also counts as a kind of a resource allocation. And then you can configure thread priority, CPU pinning, etc. And also, if you create your own threading library, you also need to support priority inheritance in your vertexes to have a real-time system. Then on the high-level software architecture, we don't rely on an executor. We rely on the OS scheduler. If you look at a small picture here in the middle of the slide, every task basically runs in its own thread, and it waits for a trigger or waits for some data to arrive and then process its data. And you have many of these tasks, meaning many of these threads running. And so which means that the OS scheduler can interrupt this thread at any moment if a higher priority task should be executed. The really advantage of using the OS scheduler is that they are very well understood. There's a lot of research out there on how to use them. There's very good tool support that helps you analyze the runtime behavior of your application. If you use an executor, there's basically no research available. There's just now some research is going on from some companies trying to understand how actually executors behave and how make executors safe, but that's just research just happening now, while with the OS scheduler, you have 20 years of experience or more. The disadvantages that you have is you have more context switches than we then execute the based architecture. So you need to make sure that your CPU are properly pinned and your thread priority is correct. To ensure that we have correctness, we use advanced tools. For example, you have thread sanitizer or Hellgrind, one from Clang and one from is Valgrind based, which help you finding data races and other problems in your multi-threaded code. And these are runtime tools. Also, there are static code analysis tools are available, like Clang thread safety analysis, which you can annotate your variables and your mutexes, and then the tool will statically tell you if you have any problems with the data race or something like that. And let's talk about testability and failure injection. So, as we already discussed, code must have a very high test coverage. And if you have gaps in your coverage, you are forced to manually inspect this code. And this is a very tedious and expensive process. And you have to constantly repeat it for every release. And the challenge is basically going back, you want to implement your own threading library. You call pthread create in here. Pthread create returns all kinds of different error codes. Now you want to inject a failure. And you need to test that code. And how can I do that now? There are classical ways to do that. For example, with macros, is a real code example from our C code, from a mutex. And you see that you have basically more failure injection code than actually production code. So using macros usually heavily pollutes the production code. And it's also very difficult to scale. Another way is to replace the shared library with a mock library. That would work very nicely with pthread. You can just write your own pthread mock, replace the shared library that injects all the kind of error that you want. You have no pollution of production code, but it can be hard to maintain, and it's not always applicable because your application might not always split up in shared libraries in a way that allows you to do that. And C++ provides some additional tools to help you with that. And I think there are two common tools how to do failure injection in C++. One is templates. So you would create a class wrapper for a function that should inject failures. And of course, in this wrapper, you need to avoid logic because else you would have to test the wrapper again. And then you would create a mock class which triggers the desired failures. And of course, you can then make this mock class configurable during some singleton configuration, so you can switch between which error the mock class should create. And then in your implementation, you would use a template parameter then to inject the desired wrapper. And then for the user-facing side, you can then hide this failure injection machinery behind the type def. And in test code, you would then use the mock wrapper as a template argument. Another way to do failure injection is using polymorphism. It's very, very similar. You would create a polymorphic interface for the function, which would inject failures. And then you implement and then you have an implementation which does a real function call. And additionally, you need to have a mock implementation which injects the failure. What you then also need, or one way to do this, is to have a factory which selects either the real or the mock implementation based on some configuration. And then, of course, your implementation of your production code then needs to use this factory to get the interface. And then in your test code, you can then, using this global configuration to enable the mocking behavior. Okay, that's so far. Thanks so much. Any questions?
Hi. One little question. So what is your approach with the containers? Like, do you wrap the standard containers, or have you like created your own containers from scratch? And what was your experience?
Yeah, so because we are able to get a already certified C++ standard library, we don't want to write our own containers because then we need to certify all that code, which is very expensive. So we try to reuse the existing containers. That's why we use an allocator-based memory pool for the containers. For the map, for the set and the map, for the vector we also use an allocator, and the string we had to implement ourselves because you cannot implement a stack-based storage allocate in C++14.
When analyzing your memory safety, do you have any tools for measuring the maximum stack potential maximum stack usage from any thread in particular?
Yeah, you can. You can measure how much stack you consume. So how you usually, I should repeat the answer, sorry, the question, sorry. So how do you measure how much stack you consume? I guess that was the question.
Well, yeah, how you would do it, and if it's actually something that you do, or if not, why not?
Yeah. So I said, do we measure stack memory consumption? And if not, why not? So we have tools to measure it. But if you would exceed your stack, your application would crash. So what is important here that you have full branch coverage. So that if you have full branch coverage, you know that you went through all the branches and you know you know your maximum stack size. Yeah? And this is how you can determine your maximum stack size. So it really depends on how well is your code tested. Yeah, go ahead.
Hi. Michael Wong. I just wanted to find out why you chose to start off with the Joint Strike Fighter specification. Because it's an older specification. Yeah. It's good because it's done by Biana, but it's based on an older C++.
No, we don't use the Joint Strike Fighter specification. We actually use AutoSAR C++14.
Okay, that makes more sense because I saw in the example you used JSF.
It was just like an example, like 2005. People claim tool support is bad. 2019 tool support is still bad.
It's still bad, but yeah, okay. No, that's
just like an anecdote.
Okay, no, that makes sense. I want to invite you to join SG12 because that's where I'm living, to try to bring some of these exact issues and solutions in, because that's what we're trying to do is to try to make those make C++ better for safety critical. All right.
Okay. Thanks.
Hi. So, what do you think is better, converting an existing library or code base into a safe code, or creating one right from scratch?
That really depends. So for example, there's boost static vector, that you could use, but it's huge and it's very complicated, And there we just implement our own simpler, slower one that is easy to understand. But for example, the memory library, where there's a lot of small details going on, like determining node size. It's pretty complicated logic. We decided to reuse existing code and just to cut the code down. So I think it's a case-by-case basis, but if the code is huge and really complicated and really highly optimized, usually you try to just implement something simpler. Like in safety-critical code, keep it simple even if it's a bit slower.
Makes sense. Also, you said about the qualified toolkit. So what would you use for testing in that case?
So what you need to do basically is you need to do a tool qualification. So for every tool you need to say what happens if the tool doesn't work properly and would that introduce a safety hazard. And so there are coverage, and that's actually a bit an open question that we have. There are code coverage tools that are qualified, that have a stamped by TÜV that says this thing is qualified. I think LCOF is not. But these tools that are qualified are horrible to use for the developer. So what we're doing is basically, or most likely what we will do, it's not decided yet, but most likely what we will do is we will take, use LCOF for the developer so they know, okay, my code is garbage, and then to generate the report, we use a different tool.
So in your
fault injection example, the polymorphic one, how do you avoid dynamic memory allocation? Because you need the base base case reference or pointer.
So sorry, I got such sign that the session is over, so I'm out of time. But I'm happy to answer your question later. So I will be around. Sorry.